All right, Jim, I want you to picture it's summer.
Okay.
You're a kid.
Okay.
It's evening time. It's not exactly dark, but it's not really light either.
Mm-hmm.
You look over by a bunch of trees, and what do you see in the distance?
Fireflies.
How'd you know?
You would not believe your eyes.
I'm going to get a copyright on that. It was so good.
Yeah, I'd be like, that's not just like that guy.
Yeah.
That did that.
Amazing. Yeah, I was here at your house and saw fireflies in your front yard.
That's right. Did that like little walk around?
I don't remember seeing them that day, but definitely it was one time we were recording, and maybe it was then. I don't know. It was a time that I was here in an evening,
Mm-hmm.
and I was like, when was the last time I saw fireflies? And that day was when I decided that we were going to do this episode.
Nice.
And
That's
I've
awesome.
seen them since then a few times.
Uh-huh.
And it's very exciting.
Yeah.
So have you ever wondered about the chemistry of fireflies?
Yeah, I mean, I guess I, as a kid, wondered about fireflies, but I wouldn't have been as specific as to wonder about the chemistry.
Right.
You know,
You're like, how do they do that?
But I guess, that is what a bit of that childish wonder we lose. I hadn't really thought about it. I do know, I feel like there's other animals that I've learned about, like the bioluminescence of, like the fish that are like way in the deep. But I don't think I've ever learned about fireflies.
Well, today's your lucky day.
Nice.
Let's get started. Let's light it up.
Yeah.
I was trying to think of a
Let's get lit.
pun. There it is. Let's get lit. Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast that helps you understand the chemistry of your everyday life.
We're going to say hod past.
Yeah. One of my kids says cob past.
Cod past.
Yeah.
Yeah, sometimes Mason and I call it that because we think it's cute.
Yeah.
Okay, so I will want to say first, before we start, I want to give a shout out to Ash. She's one of our community members. And she has been behind and just like binging the podcast ever since she joined the community, and she officially caught up.
Nice.
So that's fun. So I wanted to give her a little shout out.
Ash, that's quite a feat.
It really
that you have
is.
accomplished.
Yeah.
There are people I'll introduce to the show now in person. They'll find out that we have a podcast or whatever. And I'll send it to them, and I usually say, honestly, just swipe through and pick one that interests you, where you can tell from the title. If your podcast app has the deal where you could search.
Yeah.
But pick something that's like a topic you already are interested in. It's kind of like, oh yeah, I wonder about that.
Yeah.
And I just don't expect people to go through all of them at this point. When we're in the 200s, it's like, that's a lot.
That's amazing. But I have podcasts that I do that I find them and I love them, and I'm like, and I can listen as long as I want. But then when you catch up, it's kind of bittersweet.
Yeah.
So to soften that blow for you, Ash, we decided to just give you a little shout out here.
Nice. Yeah.
Yeah.
Well
soften
deserved.
it. Yeah. Good job. Also, speaking of, no, this is off topic. I was going to ask you about Seinfeld because you never finished that, right?
I have not. You're right. I've never watched the finale.
Because you just never wanted to be caught up.
Yeah. It's like once I've watched it, I've seen every episode.
Yeah.
So I still have not seen every episode.
I love that. Okay. This is all that's really off topic, but I do want to do the chemistry of fireflies because I did get really excited when I saw them. And the first podcast I ever listened to was Radio Lab.
Nice.
They had an episode on emergence, which is like when you have the individual, they're not as impressive, and then sort of they come together. And I'm pretty sure they talked about fireflies on that episode. And so it's kind of like full circle because now I have a podcast.
Yes. I wonder, I probably have listened to that one way back in the day.
Now I'm worried that it's the emergent. They definitely talk about ants on emergence. Let's see. Okay. Anyway, but it could have been something else. It could have been a different episode, but that was the first podcast I ever listened to. So back to it. This is a full circle moment for me, and I'm really excited about it. And I'm going to start with a simple overview of the chemistry, and then I'll give a more detailed version.
Okay.
So you're right. The light that we see from fireflies is bioluminescence.
Okay.
And there are several different mechanisms of bioluminescence, and they have actually evolved separately. It's not like, oh, and they're all really similar to one another.
Mm-hmm.
They all have different mechanisms. So it seems like different species have evolved this like ability to give off light for different reasons by different pathways.
Mm-hmm.
So that's kind of cool. It's like separately, a lot of different things found it would be useful evolutionarily to have this ability to make light.
Yeah, and then found different routes to it.
Mm-hmm.
Wow, that's crazy.
I know. Okay, and so fireflies naturally produce a chemical. It's really a class of chemicals like that are called luciferins.
Okay.
Lucifer, meaning the devil. Not the devil though. It actually means to bring light.
Yeah, and shining one is what that means in the like story.
There you go.
Side, yeah.
There you go. So shining one, luciferin, but I think it's called luciferin more often, or luciferin.
Okay.
There's a class of those chemicals that happen in animals with bioluminescence, but they don't really distinguish it. So they just call it the luciferin compound or luciferin compound. So essentially that reacts with an enzyme that's designed specifically to react that with oxygen. And after a series of reactions, it makes a new molecule, which then emits light.
Okay.
So that's the super simple version of it.
Okay.
It's basically like this thing plus oxygen, magic happen.
Got it.
Okay. But it really is more in depth, of course, than that. And there's lots of cool chemistry involved. And then there's also several applications of like places that they're using this in real life. So I wanted to start with that brief overview of like, okay, they make this molecule and then go a little bit more in depth and do the little chemistry lessons.
Okay.
And then after you get tested on your lesson and tell it back to me, then I'll give you some fun facts.
Deal. Sounds good.
As like a little treat.
Nice.
Little reward for you.
Like a treat for my brain.
Yeah, exactly. Yeah. Okay, so like I said, this reaction starts with the molecule luciferin. And it actually on its own, it can absorb and re-emit light. So it can sort of glow on its own. So you might think like, oh, well, is that all that's happening? But fireflies usually light up at night, right?
Right.
Light up at night when there's not very much light to be absorbed, so not very much light to be re-emitted.
Right. And do we know if they light up during the day, but just like not visible?
I don't know if they light up during the day, but it's not visible. I don't know about that, but I do know that they can control when they light up. Okay. So I could see them
not doing it when it's daytime.
Yeah.
I see. Okay.
Because it probably wouldn't serve much purpose.
Yeah.
And it will take away energy from them.
Yeah. Okay.
So, but you're right. And it could be that if there's luciferin that can absorb light during the day, that they are like maybe slightly glowing during the day. But it wouldn't be that like blinking that they do. Okay. So, and the organ that they do the blinking in is called the lantern. Isn't that cute?
Nice.
Okay. That was kind of an aside.
As somebody was like thinking when they were studying that, they're like, I could name something really ridiculous and like, I could just go like something very Latin or whatever, but why don't we just call it
the lantern?
It's like, let's make it just understandable to people.
It's cute. So the light happens. So it's not just that. There's a lot more chemistry behind it. So there is an enzyme called luciferase. Okay. And ACE is oftentimes the ending that goes on enzymes. And enzymes' job in science is basically to help facilitate a reaction and help a reaction happen more easily.
Okay.
So usually it'll be like sort of a protein with what we call a binding site, where one molecule can come in and bind into that enzyme.
Okay.
And that binding site of the enzyme is it like has the exact atoms in the exact functional group arrangements that it needs for the molecule that it's looking for to bind in, and nothing else.
Okay.
So luciferase is specifically designed for this luciferin.
Okay.
But what's really cool is that actually the luciferin binds and one reaction takes place, and then the luciferase rotates 140 degrees and essentially makes a new binding site so that a second series of reactions can happen.
Whoa.
I was like, it's like a transformer.
So which one is it? Luciferase that rotates, you said?
Yeah, the luciferase rotates 140 degrees to make an essentially new binding site.
Okay.
Isn't that amazing?
Yeah, that's weird.
And so I just thought about it like a little transformer, that it's like, oh, you had your first reaction.
Yeah.
New binding site, new things can join in.
Interesting.
So the first reaction is the luciferin reacts with ATP. That is short for adenosine triphosphate. It's really commonly used as basically a way to move energy around in cells. You've probably heard of it before.
I have. In fact, that's like almost what all of AP biology revolved around when I was in high school. It's like ATP synthase was like the thing.
Yep.
So I hadn't thought about that in a long time.
Well, that happens. And basically what it does with the luciferin is it makes a new, more acidic molecule.
Okay.
So that luciferin reacts with ATP to make a new acidic molecule.
Okay.
And I want to take a break here to do a little acid-base review. Do you remember what happens in an acid-base reaction?
Well, an acid-base reaction. I remember having a hard time on the like the intuitiveness of like how to describe what an acid is and what a base is. I remember it always trips me up. It's like acids want more dang it. What I do remember is that whenever they combine, they react initially, and then equilibrium is reached basically, where the like, I guess the moving around of electrons happens, and after that they've basically, in the case of like vinegar and baking soda, they just net water afterward because the things that have like reacted and foamed up have evaporated and gone away or whatever.
Yeah.
But what I always struggle with acids and bases from way back on our very first episode about them, which I think was about baking soda and about baking powder, was getting my head wrapped around that acids were kind of different than I thought they were. And it's that one of them lacks something and wants something, and one of them wants something and lacks the other thing, or whatever. And I'm struggling there to remember in the moment.
So a lot of times the very first definition of acid base we learn is an acid gives up protons.
That's right.
And the base we often learn makes hydroxide ions.
Okay.
And then as we get more advanced, it's like an acid gives up protons and a base takes protons.
Okay.
And then as we get even more advanced, when the acid gives up that proton, it's leaving behind the electrons. So it gives up a hydrogen atom, but the hydrogen atom it does not bring its electrons with it.
Okay.
So it leaves the electrons behind. So the acid ends up getting extra electrons.
Got it. So it ends up at becoming more negative, having more negative charges.
Yes, and usually something more negative that's more reactive even than, what gets left behind on the acid, it takes the proton.
Okay.
So usually there's something basic that will take the proton away, and when it does, the acid is left with what used to be bonded to the hydrogen, made up of two electrons. This bond gets left behind, and so we sometimes call the acids are lone pair acceptors because they end up with a pair of electrons.
Got it. Okay. So acids start out basically ready to give up a proton.
Yep.
And so,
which is like a hydrogen atom minus its electrons.
Okay. So they're ready to get rid of the hydrogen and keep the electrons.
Yes.
And so after a reaction happens, they end up being more negative.
Mm-hmm.
But before that happens, are they more positive or are they just more normal?
They're kind of more positive.
Okay.
That hydrogen specifically is positive.
Okay, got it. And so, and this is what really I remember tripping me up, because I, for some reason, just thought of acids seem negative to me. You know what I mean?
That is so interesting.
And that's like one of those things that's hard to shake. We haven't talked about acids and bases a ton, as much as we have like proteins and polymers and stuff. But I remember when it's come up, I have to like think it's not how you think it is. And even so, my brain would have thought, before we had talked about it, never would have thought about what was going on at the molecular level in the first place.
Yeah.
So,
well,
anyway.
That's the whole point of the show, is to bully you into that.
Yeah. Oh, I noticed you were doing that.
Yeah.
I didn't realize that was a part of the show, though.
Yeah, just bullying you into thinking about chemistry. That's all of it.
God, that's what the show's about. Okay,
right,
got it.
Right.
Okay.
And that's what I do to my students. I'm just in here like, you think about chemistry.
Yeah.
No, I don't do that. I'm like, please think about chemistry.
Yeah.
And think critically about it. Okay, so this acid gives up it once we have our luciferin reacts in the first step with ATP to become more acidic.
Okay.
And then in the second step, that acid will give up its proton. A base comes and takes it. And so then it leaves what started out as our luciferin with that lone pair of electrons. So now it's negative.
Okay.
So you're like, acids are negative. This acid does end up being negative after it gives up its proton.
Okay. And then is it still an acid at that point?
Nope. After that, it becomes either a base, or sometimes we say that the thing that is likely to attack is a nucleophile.
Okay.
So it's a thing that's like going in and like, it's going to take its electrons and bond with something.
Got it.
So it's the attacking group. Okay. So let's see. Where was I at? I got distracted because we had a little bit of technical difficulty.
Just a little screensaver came on. No big deal.
Oh, okay. Here I am. Here's my notes.
Okay. Got it. So wait, this is after the luciferin and luciferase?
Mm-hmm. Is in the luciferase. This is happening in the luciferase.
Okay. Got it.
So the first step gives it the ATP, and then the next step, it has a base reaction.
Okay.
A base comes and takes the proton. And now we have this new negative species that's going to attack actually oxygen.
Okay.
So it's going to react with oxygen, and there's some debate about like how that actually happens. It's like, what's the oxygen doing? Why would it react with the sort of normal oxygen? But what's certain is there's an acid-base reaction, and then this new molecule reacts with oxygen somehow.
Okay.
And it makes this crazy thing. There's like the rest of the molecule doesn't really change, but right at the point where the hydrogen was given up and it reacts with oxygen, now we have a functional group that you almost never see in chemistry. And that is because it's so unstable.
Interesting.
And what we have is, in chemistry, you sometimes see rings. So you've probably seen a 6-membered ring.
Uh-huh.
In chemistry, you think about like hexagons. You see those in chemistry.
Uh-huh.
Like 6 carbons will line up nicely.
Mm-hmm.
And sometimes in chemistry, you can get 5-membered rings. 6 are the best, but 5 carbons together, it's like okay. But 4 carbons and down don't happen very often, because when bonds form, they want to have as much possible room around them so that the electrons aren't getting squished together.
Okay.
So if you think about it, electrons are negative.
Mm-hmm.
So they don't want to be really close to other negative things. They repel each other.
Okay.
And so because of that, bonds will sort of like spread out as much as they can possibly to get away from each other.
Okay.
And so if you have something in a ring, instead of having, 3 things being able to spread out wide, they have to be close together. And that's a lot of electrons in a small area. So like you don't really get 4 rings made up of 4 carbons or rings made up of 3 things very often.
Okay.
And if you do, they will react really quickly.
I see. And it's because of the electrons being that in proximity to each other?
Yeah, so we call that ring strain.
Okay.
So there's the ring strain is made up of like there's two different things. It's kind of like the shape is bent out of place, and they don't want that. Like the shape of the atom is like being forced into this ring shape instead of being able to take its natural spread out.
Mm-hmm.
And then those electrons are repelling one another.
Okay.
So because of that ring strain, that's like, ooh, it's a good example is like, if you've ever had a pair of pants that's a little too tight, and as soon as you button them, it's like trying to push out against your button.
Mm-hmm.
It's like your belly's trying to escape.
Yes. Like you've been able to make this work, but it is definitely under tension.
Yes.
I see. Okay.
And the littlest bit of something will bust it open.
Mm-hmm.
So that's what we have in these 4-membered rings.
Okay.
And it's a special 4-membered ring because it's not just 4 carbons. It's 2 carbons and 2 oxygens from the oxygen molecule that it reacts with.
Okay.
So that makes it even worse because oxygen has lone pairs on it.
Okay.
So oxygen just naturally in its like neutral state has extra electrons around it already. So there's a lot happening in this little 4-membered ring.
Okay.
And it has off of one of the carbons, there's another little functional group off of it. So you're like, what is happening? There's so many things happening. And this functional group, this 4-membered ring with the 2 oxygens, 2 carbons, and then off of one of the carbons, you're getting another oxygen bonded in. This is known for being responsible for bioluminescence.
Okay.
So it's associated with bioluminescence. The only times you really see it show up in nature is like as a precursor to bioluminescence.
Okay.
Because it's so unstable that it will break down. And actually the carbon and 2 of the oxygens will leave.
Mm-hmm.
So it gives off CO2 and it gives you this new, slightly more stable molecule.
Okay.
But there's a caveat with this slightly more stable molecule.
Mm-hmm.
In chemistry papers, when this molecule is written out, there's a little asterisk next to it.
Okay.
And that asterisk means that the electrons present in this molecule have absorbed energy and they are already in an excited state.
Okay.
So I'm going to stop for our new listeners. This might seem kind of like a heavy episode, but a lot of these are topics we've talked about before, so that's why I'm going kind of fast. Electrons in molecules, I guess even like going to the very beginning, is molecules are made up of atoms that are bonded together, and their bonds are formed by electrons being essentially shared between 2 molecules, or 2 atoms, I mean. And those electrons, they're not like stuffed in one place. They can kind of move further away or closer in. Electrons have the ability to move around. They're sort of like free floating around in some pre-designated areas. And if you put energy in, they can sort of move further out of their range.
Okay.
And they have more energy in them, and we call that the excited state.
Okay.
And we've likened it before to if you give a kid some snacks, then that kid needs to run and let all the energy off, right?
Yeah.
So this molecule is essentially formed in the pre-snacked up phase.
Got it.
So it already has energy stored in it.
So it has already eaten the snacks, basically, but it has not done anything yet.
Yeah, it's like born full of snacks.
Got it. Okay, got it.
And as soon as it's born full of snacks, it will let off light as it's releasing that energy. That's how it gets that energy out to bring it back to a normal state. It's like heightened. And so it releases light as the electrons let off that energy. And that's the light we see from fireflies.
Okay.
So it's kind of a complicated step. So there's the acid base. There's a reaction with oxygen, oxidation, we would call that. So acid base reaction, oxidation reaction. And then there is electrons, which are in a high energy state because of how unstable that original molecule is. Something about the way it breaks down is and loses one of the carbons and the oxygens from that ring. It's like we start out high energy.
Mm-hmm. Got it.
And then it lets it off to give out light. And all this is aided by this luciferase that holds it in place and brings the other things it needs around and facilitates that reaction.
Okay.
And there's lots of studies about this, and I feel like they're learning a lot about fireflies even still, but it's like, okay, this luciferase seems to be shaped in this exact way to bring oxygen in, and what's the state of the oxygen? Why is this negative thing reacting with oxygen? So there's lots of questions, but the main idea is those kind of key points is we get an acidic version of luciferin, and then it goes through acid-base reaction, then it oxidizes, then it lets off light.
Okay.
Okay.
Dang, this is going to be a struggle for me.
It is pretty late.
Yeah, I think...
And it's a heady topic.
I think the lateness could be playing a factor. We also haven't recorded in 5 weeks?
Yeah, it's been a little while.
Yeah.
And we accidentally had friend time.
Yeah, oops.
Before we started recording, we chatted.
Melissa and Mason just had to bring over some ice cream.
Whoops.
And, I didn't want to be rude, so I was going to eat some. So
listen, we're good friends. We show up with ice cream.
Yeah. Get yourselves a co-host like Melissa who brings ice cream. Actually, sorry, she's already my co-host, so sorry.
Yeah. Sorry, I'm taken. I will not be co-hosting any other podcast.
So we have the luciferin.
Yes.
It is already there.
Mm-hmm.
It is already known, right? You said, is this the one thing that's known, is named in this way because it's associated with bioluminescence in general?
Mm-hmm. It's a class of molecules. Classy. Dude. Mm-hmm. Classy.
So the luciferase is an enzyme.
Mm-hmm.
It comes and links up with luciferin.
Mm-hmm.
And then it immediately reconfigures, right?
I think it might reconfigure after the initial reaction.
Okay. And the initial reaction...
it can do the ATP and then it
Okay. The initial reaction is the acid-base one?
I think that... I'm not clear on this. I tried to find out when the rotation happens, but it was only mentioned in one paper. But the initial reaction is it reacting with ATP to make it more acidic.
Okay. Got it. I got that backwards. Okay, so it has the ATP reaction first, and then it seems to reconfigure, rotating 140 degrees, new binding site, is that what you called it? And then we have the acid base.
A separate base comes in, takes that hydrogen.
Takes the hydrogen away from this acid. Now it is basically a base.
It's reactive. It's got extra electrons. Which allows it to then react with the oxygen. After that, once that has happened, it creates... we get a weird ring, and it's under tension. Lots of tension because all the electrons are so close together.
It's four. It's like a four. I guess that would be a ring, like a square. It's
like a square.
Yeah. Like a square, which is not a thing that wants to exist very often. And it also has a functional group at this point on the side.
Yeah, it does. And the square is made up of. Can you remember what 4 atoms?
Carbon. And it's reacted with the oxygen. So oxygen is one of them. And
it's 2 carbons and 2 oxygens.
Oh, dang, okay.
So you already got it right. I was like, do I let him suffer?
I was like, what else was there? I just didn't.
It's just carbons and just oxygens.
I should have let myself think, that's all she said. And that's what it is.
Yep, that's it. That's all I said. That's all.
I really was like, wow.
2 of each.
What else was there? That's so crazy that I just... Okay, so 2 carbons, 2 oxygens. And at this point, it is... After those things have happened, the reactions have happened with oxygen, we have this ring. It's under tension. It has a functional group. It is already... It's asterisked, right? At this point.
Not yet.
Oh, not yet.
It's just super unstable.
Unstable. Okay. Unstable.
It's like, it's straining against its belt buckle at this point.
Yes, straining against the belt buckle. Okay.
Maybe a good example would be the ring. It's like a pregnant lady. The baby is straining against the belly, and then it breaks down, and the baby comes out. But it's like if you pre-fed that baby with sugar.
I see. Okay. So getting from the state we're in now, where it's high tension, not stable.
Yes.
To the next thing, I'm already forgetting what gets it to the.
I think it just spontaneously breaks down.
Okay.
Because it's so unstable that it just can't live in that state, and so it's more stable for one of the carbons from that square and two of the oxygens to leave.
Got it. Okay.
And they make carbon dioxide, exactly like you were talking about. What happens a lot in acid-base reactions? They make carbon dioxide. The carbon and two oxygens leave.
They make like a carbon dioxide and.
Nope. He tried. And leaf. Wait.
Yeah.
Well, leaves do they breathe in carbon dioxide? Yeah. Sorry, I was going to say. But no, they almost.
Yeah.
So the carbon dioxide leaves. And it just naturally, it's like, okay, we can't live in this 4-membered ring. It's too much tension. The strain is too great. It breaks. And the high energy baby is born.
Got it. Okay. I was like, I knew we got to that point, but I was forgetting what happened because it's not a something coming and doing a thing. It's this just has to happen because it can't exist in an unstable. We talked about that a lot. Like things want to be stable.
Yes.
So they will try to find a way to be if they can.
Well, and this one was hard because I was like, is it interesting to talk about every single reaction that happens? Because there's so many. I could have just said and then 4 reactions happen. But I think it's interesting that one's an acid base that we've talked about before. And another is making this functional group that we've talked about before, but a new type of functional group that's really unstable. And I think that's interesting. We haven't had a chance to talk about ring strain before. And I think that's interesting. And then fun to share. It's like, hey, guess what? Electrons don't want to be near each other. And so sometimes they'll just kind of burst themselves open.
Yeah.
And then also that we can have molecules existing in the excited state from the get-go. So
then it's excited state. It's more stable, but it's excited.
Yeah. It's like, we got a little bit better, but we're still up there.
And I guess they're able to control this, you said, but does it immediately start to try to come back down from its heightened state? So it's, once this part exists, it's already going to come back down.
Yeah.
And give off light.
Yeah. Electrons can't stay in their excited state for very long unless, like we talked about with the glow in the dark stuff, sometimes they can't find their way down and then it will last longer.
Right.
But in this case, they're able to find their way back down quickly, and so they'll relax back down quickly.
Got it.
And it may be that I was going to say that if there's any luciferin, maybe we're seeing that, but the majority of what we're seeing is this end product, which I believe is called oxyluciferin because it's gotten that oxygen.
Got it.
Okay, and you were asking okay, so now that they have this thing, it just automatically happens. Yes, but oxygen is a key part of this reaction.
Right.
And oxygen is also a key part of mitochondrial, the function of mitochondria in cells. And so what fireflies will do to control their lighting or not lighting is they will suppress their mitochondria. Say okay, mitochondria, we're using our oxygen elsewhere. And so the mitochondria won't work essentially. And they divert that oxygen over to react with the luciferin to make our glowing compound.
Got it. This oxygen they already have in their cells, in their body. So it's not like a long as they're taking more in, they're just redirecting oxygen. Okay.
Yeah, they suppress the function of their mitochondria so that they can focus on making this reaction happen instead. So they're kind of controlling it.
You know what's so insane?
What?
It's like cells are so small, and we know that as we learn about. And now we're talking about, inside the cells, the atoms of oxygen that the mitochondria are using, so these atoms are even smaller, of course, are being rerouted to something to be used elsewhere. It's just weird to think of like cells are already tiny and atoms are that much tinier.
Sometimes I think about that where it's crazy, right? And we're talking about this and we're like, okay, and so then the Firefly suppresses this and this happens. And you're like, does it do it on purpose? Does it know? Is it thinking, okay, time for me to light up, so you don't do this?
Yeah.
And also there's mitochondria and like oxygen atoms like all over our bodies.
Yeah. Yeah, it is weird to think of there being tons of pockets of oxygen throughout all of our cells.
Weird.
Very weird.
Science is so cool though, right? It's like, wow. And people figured this out. They figured it out and now they know how fireflies work. And one of the papers I read was they were trying to study the flow of oxygen. I don't exactly remember what that particular paper's end goal was, but they basically took these teeny tiny x-rays of like the air tubes that oxygen moves through is called like brachial, I think, brachia, which is similar to what it is called in our lungs too, I think. And they like got the smallest like microscopic x-rays of what the air exchange tubes inside a firefly look like. And I was like, that is crazy and incredible. And some of the fun facts we'll talk about show why that matters. Sorry, carry on.
I was going to say just that it's amazing that we know anything at all in a way, right?
Oh.
And that it also makes it not that surprising that there's so many things we don't know.
I know.
It's like we figured out that there are atoms of stuff and that they're in everything, and we figured out that there's cells and that they're all over our bodies, and there's plants and animals both have them, and there's some similarities between them and some differences, and they need these same atoms that we talk about in other things. They're made up of atoms, and in this case, the fact that they figured out that this is one of the things that's going on in fireflies is insane.
And they even figured out what state the oxygen is in so that it can react with them.
Yeah. So weird. But then to think that there are many things that we're like, how does that work? And maybe it's still being figured out. Like we've talked about how many iterations of mosquito research have been happening.
Yeah.
And like, we're figuring stuff out. It's just that there's also still plenty that isn't certain.
Yeah.
That's we're working on. I'm like, no wonder, because this is stinking hard. Like, it's all tiny, and we're like, these mysteries are so hidden.
Yeah.
And not obvious.
But very cool.
Very cool.
I'm glad you love learning, Jam.
I do love it.
And probably most of our listeners also love learning.
Yes.
Okay, so we know that they can divert the oxygen away from their mitochondria, but also each individual species of firefly will have its own unique intermittent flashing pattern.
Okay.
And so scientists think they're using this flashing pattern to attract mates or maybe even to warn predators, like, because they can put out some toxic things. So it's like, you eat us, you're going to die. But there is crazily one species of a female firefly that mimics other fireflies and then is like mimics their light for a mating pattern and lures male fireflies to itself and then eats them.
Whoa.
I know.
That's crazy. So what do fireflies eat when they're not doing that?
I don't know.
Little plants or something like that? So like,
I don't know. I didn't look that up even a little bit.
I feel like there's some bugs that are eating other bugs and some bugs that are eating plants. You know what I mean? It's like the two kind of things there. So that's crazy. There's some firefly that's like, I'll just eat other fireflies.
Yeah.
Huh. Wow.
And I'll figure out their specific flashing pattern. I'll mimic them.
Yeah.
And I'll lure them here and then I'll eat them.
Yeah, that's crazy.
It's crazy. Okay. Now, so we figured all this out and you might be thinking, okay, are we just learning this for learning's sake? Like, why does it matter that we're learning about how fireflies work? Well, tumors often produce hydrogen peroxide and they often produce more than normal, you know, because our body does have hydrogen peroxide. We've talked about that in a lot of episodes.
Yeah.
But the hydrogen peroxide, just for people who haven't heard some of those episodes, it's a hydrogen bonded to an oxygen. And that oxygen has a bond to another oxygen. And then that oxygen is bonded to a hydrogen.
Okay.
And it's really reactive. It'll like break down really quickly.
Okay.
If it can. It's those oxygen bonds to one another are just pretty reactive anyway, like single oxygen bonds. So anytime you have two oxygens together like that, they're trying to react.
Okay.
Okay. And hydrogen peroxide can similarly trigger this reaction in the same way that the oxygen does. And so scientists have made it to where they can identify tumors and have them glow through the skin of mice so that it's easier to take images of them and to keep track of tumors underneath the skin through tissue because it's glowing, because they've like put literally probes in that are designed with this Firefly enzyme and luciferin that when they encounter the heightened amount of hydrogen peroxide around tumors, they can study them and look at them and see them more efficiently.
Yeah.
Isn't that crazy?
That is crazy.
And so for right now, just doing that in mice, it's like, well, you can study the mice longer term and see the development of the tumor in the mice more easily with imaging and you can watch like how much is it using hydrogen peroxide, things like that. But that's not the only thing. They've done really similar things for like, okay, so if we have this much ATP at the beginning to make that reaction happen, then we know that much ATP is required for this reaction. So we can measure output of ATP in other cells. So they like are making lots of little probes and measurements and all these like analyses and learning about cells using bioluminescence.
Okay.
And one interview I read with someone, he used a different bioluminescence that used calcium. It was not in fireflies. It was in other species, I think, of fish. And like that's part of how they figured out that calcium was a huge transporter in our bodies. It's like it's transporting things and signaling.
Yeah.
So they're using these bioluminescence biological reactions to study our own biology. And so sometimes I feel like when we get in the weeds of things like this, you're like, this is so cool, but why are we wasting money studying fireflies?
Yeah.
It's like, surprise, you can use firefly magic science to then study other areas of biology and learn things like, wouldn't it be great if you could just inject firefly dye in you and then if you have a tumor, it'll go there and light up and you're good?
Yeah.
That'd be amazing.
Yeah.
But you can't do that if you don't know how fireflies work.
Totally.
So also kind of scary. What if we could like inject our veins with that and it goes through our whole veins and then if one area starts glowing, it's like tumor. That would be crazy. I don't think they're there yet, but wouldn't that be amazing?
That would be crazy. This reminds me that I'm pretty sure this is the headline, but I didn't know anyone connected to fireflies. But I saw this I guess you could say it's a meme, but it wasn't really like memes are like repeatable, right? This is more like one screenshot, but it was like a headline from a news article that said, scientists have figured out how to make the tumors in mice glow. And then the comment below, I did not realize this was going to be cool. The comment below it, like that's one of the screenshot, it was just, is that good? It's like great. I remember loving that because it was like, without any context, without going and reading the story, just the idea of like, scientists have figured out how to make the tumors glow. It just sounds like, oh, okay. Do we want the tumors to glow? Like, just the idea of like walking in off the street and not knowing any context about why this was being done and what it might help with, but just seeing a headline only.
I love that. That's hilarious.
Yeah.
Excellent. Okay. Oh, the other thing I was going to say is
Mhm.
we said luciferin as a class, but different molecules within that class of molecules can make different colors. So that's kind of fun. And then I was also going to share about how bioluminescence is developed independently, but you brought up bioluminescence. So I already told you that.
Bioluminescence, one of the coolest little phrases, words to just know.
The first time I ever heard that word was when my sister did a summer internship in an island in Alabama, and she like ran out into the water and ran her hand through it, and it like lit up. And I was like, that's crazy.
That is crazy.
So, that's it. And you already explained it back to me. So I thought I would wrap it up with some categories.
Okay.
And my category is either you can pick a nostalgic summer feeling. Like what is something that you're like, oh, this is so summer. Or what is your favorite light up thing?
Ooh. Good questions. I think thinking about, you talked about not just summer stuff, but also when we were kids, you know? At the beginning with the Fireflies and stuff like that, and nostalgia, of course, would be that. But one of the things we would do when we were kids, which I guess I'm kind of surprised that we did this because it's so hot in Texas.
Yeah, but when you're a kid, you don't care.
I know, isn't that weird?
Yeah.
It's
like it gets hotter and hotter, but it's really like, no, you're getting grumpier and grumpier.
Yeah.
And also hotter and hotter, but whatever.
We would do this. My grandparents lived in this retirement community, not like a facility, but like a neighborhood, you know? And it was divided into these like circles, like where the street was basically a circle. And then the houses were all on the like inside of the circle. And in the middle of the circle was a little park kind of thing that was like not huge, but they could all share it and stuff. When my cousins would come to town, at some point in the summer, almost every summer they would, we would play a game that's kind of like hide and seek called Spotlight. You ever heard of this Spotlight
No,
before?
I don't think so.
Basically, it's like you play larger scale, and one person is the seeker, everyone else is hiding, just like you would expect. But when you're playing larger scale like that, what happens is if you're just seen at all, you are it or whatever. You've been tagged. But these games are long. Each round is longer, and so the whole point is to not be seen. But you can move around. You're not hiding in one place. And so because of the way this circle situation was and stuff, I think originally Spotlight was probably meant to be like you play at night, and if the flashlight shines on you, But we would just play it where it's like, okay, we can move around, and it's a circle, and there's a park, and there's houses.
Yeah.
We're always trying to look between things and try to see whoever is seeking where they are, and also not be seen.
Right.
That was like the most fun. Like that was like nothing was more fun, and we looked forward to every time that my cousins were going to come. We look forward to playing that game. We play it forever. And what helped a lot was that we are kids running around in this neighborhood.
Yeah.
But it's like a retirement neighborhood. So there's only like two main entrances in. It wasn't like a place people would be passing through to get from A to B. Only people that are driving around in there are people who live there, who are older and not speeding around.
Right.
So it's very safe as well.
Yeah.
But we would just run all over that retirement neighborhood playing Spotlight.
That's fun.
So fun.
That's a good one. Yeah, we played hide and seek in the dark.
Oh, yeah.
Is like what we called it, which is basically just hide and seek outside at night.
Yeah.
And that's like a nostalgic summer feeling.
Yeah.
I feel like a very summer feeling for me is like getting to be up late. Like there's something, even now as an adult, I feel this when it's like, oh, we're going to go to the movies at like 7 p.m. Or like even during COVID, we would go out as the sun was setting, you know, and we would like sit in parking lots and hang out.
Yeah.
But last summer, I think it was last summer, I went to the movies with our friend Chelsea.
Mm-hmm.
And it was like, and we just stood outside talking, and it was like, it's just, you're not like,
Yeah.
oh, it's cold, I'm going to run home and go inside. It's like, the nice things about winter are wanting to be inside and cozy. But the nice thing about summer is like, it's late and I'm out.
Yes.
And we're just sitting outside talking, and it's not super uncomfortable. It's the best it's felt all day because it's so hot in Texas during the day. And so it's like such a fun, like almost like, it's summer, we're gonna be out late,
totally.
You know, like, and the sun's not even gonna be set yet, and it's gonna be 9 p.m. You know, like, it feels like you get extra time almost, and there's like a treat feeling of that, you know. And then for me, obviously, I get summer break, so that's kind of fun.
Yeah. So you still get to hang on to that, which is cool. Yeah, it's like for several of us, unfortunately, that only existed. Former time.
But you know what's crazy is I'm more excited about Christmas break, even though it's like shorter. It just, you feel like you really worked for it, you know?
Right.
And there's something about it that's like, I love the winter break.
Yeah.
But yeah, I think staying up late, being out late, getting extra time is like a special summer feeling that has like carried over into adulthood.
Yeah.
Yeah. And also eating s'mores.
Ooh, nice. I guess ice cream's like a year-round thing, but it does hit different for sure.
It does.
In the summer.
Yeah.
I'm like a lot more willing to be like, oh yeah, I'm not gonna say no to some ice cream like we had just moments ago. But it's always good. Yeah. But I think in the summer, I'm like, man, I was sweating today, and everything. Every time I got in my car, every time I stepped outside to throw the trash in the dumpster, it's like. Everything was hot and sweaty. But,
you know, a specific type of like kid freezy pop. It's like those like skinny plastic things with just, you're like, this is just sugar water. Yeah. What is that? And like, I would never turn that down as a kid. And now as an adult, I'm like, I'm not interested in that. Yeah. So. But those were, and it was so easy to have just like a pack of those in the freezer or whatever. Yeah. But those were everything. It was like cooling you off and delicious. A delicious treat. Yeah. Not as messy. Yeah. Yeah. Sometimes they're hard to open though. Well, that was fun. Yeah. Good episode. Very cool. Thanks. And way more complicated than I would have thought. Not that I would have thought that lightning bugs, fireflies would be simple, but. Well, that's okay. You can just simplify it down to, basically there's like an enzyme and a molecule that's known for this, and lots of reactions happen, and then they let off light. Yeah. It's like enzyme plus molecule plus oxygen equals light plus new molecule. Nice. So thank you for teaching us. Yeah, of course. Thanks for listening and learning. Being willing to explain that complicated thing. If you have a question, either follow up to this or a question about something else you've wondered about. Maybe it's something similarly like summer nostalgia. Maybe it's totally different, but we'd love to hear your question, idea, whatever it is. Send that to us on our website at chemforyourlife.com. That's chemforyourlife.com to share your thoughts, ideas, questions with us. If you'd like to help us keep our show going and contribute to cover the cost of making it, you can join our super cool Chem community of patrons on patreon.com/chemforyourlife. That's patreon.com/chemforyourlife. Starts at just $3 a month. That's our lowest tier, and it gets you tons. But you'll see a lot of different things we offer, ways of us saying thank you for supporting the show, and you get an ad-free feed of the show. You get behind-the-scenes looks at stuff that we're up to. You get a monthly bonus episode just for patrons, and a bunch of things you can check out. So go look it out. Go look it out. It's not late or anything. Go look at it. We'd love to have you over there. Our community is great, and they keep the show going. They keep it free for everybody else. So even if you don't join, you can be grateful to them like we are. Once again, that's patreon.com/chemforyourlife. But if you're not able to join there, you can still help us by subscribing on your favorite podcast app, rating, writing a review on Apple Podcasts or Spotify, subscribing on YouTube, leaving a comment over there, buying some merch. A little one-time support deal goes a long way. That's on chemforyourlife.com/store. We've got a few hats still. We've got collegiate sweatshirts, other cool stuff. Check it out. Those things all help us to share chemistry with even more people. This episode of Chemistry for Your Life was created by me and Jam Robinson. And Jam Robinson is our producer. And as he said, this episode could not have been created without our incredible community of patrons. And so we like to thank them, everyone by name. So we want to shout out to Justine, Emily, Ash, Vince, Julie, Heather, Autoclave. Oh, am I out of date? Whoops, I might be. I thought I was up to date members, but maybe not. Ah, scared. Okay, there we go. Autoclave, Chelsea, Doreen, Scott, Jesse, Sierra, John, Jeanette, Cullen, Erica, Carol. Yeah, I feel like this might be out of date. Am I crazy? Elizabeth, Rachel, Latila, Katrina, Suzanne, Venus, Lynn, Jacob, the other Suzanne, Brian, Emerson, Nicole, Christina, Tim, Stephen, Chris and Claire, Chelsea, Abishai, and Hunter. And if you were an old Patreon that still got a shout out, an old community member, hey, we're thankful for you too.
I think it might not be out of date. I think it might just be sorted a different way.
Oh, maybe so.
Because it all sounded like a different order to me too.
Yeah.
Whatever, guys. Sorry, 5 weeks since we recorded last. So
yeah,
I messed up a bunch of the technology at the beginning. But I think we said your name and a few other people's names.
Yeah, I think we said probably just everybody's name. And so if you want to learn more about today's chemistry lesson, you can check out the references in our show notes or on our website.
Yay, chemistry!
Yay, chemistry!
And yay, Fireflies in summer.
Yeah, very nostalgic. We're in a little bit of a summer.